Alright, now we're looking at number 13. Same set of problems. What are the p-values for the two outcomes of the anemia study in exercise 15.1? Explain why these values tell us that one outcome is strong evidence against the null hypothesis and that the other outcome is not. What we're going to do is we're going to look at those values that we had. We had 11.3, which we found a z-score of negative 3.09 in the last problem. We had 11.8, which was a z-score of negative 0.88 in the last problem. So we have all of these numbers here. Now we need to calculate a p-value. Now a p-value is the percentage under the curve. It's the proportion under the curve that we're trying to find. And so, for example here, for this 11.8 number, the area under the curve is the area to the left, because we're looking at our alternative hypothesis. So the area less than mu. Let me see how big that area is here. And when we calculate that, we use some formulas that we're probably pretty familiar with. I did it a couple different ways to show you a few different correct ways to do this. What I did is I did the normal CDF, because if you pull out your normal sheets back from chapter 3, the graphics, you'll remember that we are going from a x value, the 11.8, to a proportion, and so we need to use normal CDF in our calculators. Our left bound is going to be negative infinity over here, and we're going to find the area from negative infinity all the way up to the value that we're looking for, 11.8. Mu is equal to 12, so we type in 12, and standard deviation is equal to 0.23. Now when you type in your calculator, you don't put that left equals or the right equals or mu or all that. You just type the numbers in with commas in between them. The other option is, since we calculated a z-score, you can just plug the z-score straight into normal CDF and go from a z-score to a proportion. So again, I just put these just so you see what I'm doing. But you go from negative infinity up to the z-score of negative 0.88. And in both cases, it should give you the same answer. I typed it in a few different ways, and the reason these are very slightly different is because of rounding error. So if you use 0.23 as your standard deviation, there's a little bit of rounding there. And these two statistics here that we calculated have a little bit of rounding error from previous problems. So that's why these numbers are slightly different. But depending on what you type, you will get one of these three values for your answer. That's going to be the proportion, the p-value, for the 11.8 statistic. 19% of the normal curve is under this. For the next one, we're going to take that 11.3 value, or the z-score of negative 3.09, and plug it into the same formula, and we'll get the results to be somewhere near 0.001. Now this one here, times 10 to the negative 4th, actually if you round it, it's going to be 0.001 also. So all three of these answers are almost the same. You'll get one of these three depending on what you type in your calculator. So I'm going to go ahead and highlight that in green. Now you can see how small it is, and that's because the area under the curve is whatever is under the curve to the left of that point, which is very, very little. And so that's why that area is so small compared to this 19%. This is 0.1%, very small. Now they ask the why part of the question. Explain briefly why these values tell us that one outcome is strong evidence against the null hypothesis and that the other outcome is not. The reason that this one here is strong evidence against the hypothesis is because it's such a small proportion due to randomness that could cause a number like this. So let's say I did this study on these children, these 50 children, and I got 11.3 as my result for their anemia, or what was it, their hemoglobin levels. And now I want to say, well, if the mean is in fact 12 of the population, there's only a 0.1% chance, or proportion of 0.001, that I would get this number by pure random chance. So more likely than not, I got a number that proves that 12 is not the mean. So that's why that outcome is strong evidence against the null hypothesis. This is strong evidence against the number 12. The 0.001 is very, very unlikely to happen from randomness. On this one here, there's a 19% chance that you could end up with this number of 11.8 just from randomness, if in fact the mean is actually 12. So in that case, it's hard to say the mean is not 12. The mean might not be 12, but you can't reject 12 as a mean unless you have stronger evidence than that. A 19% chance of randomness causing that is not good enough evidence.